In the last lecture, we showed that the tensor product of two R modules exists. In this lecture, we're going to prove some basic things about tensor products and deal with some key basic examples. So our main reference is still going to be Conrad's notes on tensor products, section 3. Theorem 3.3 is about generating sets for tensor products. Let's say M and N are R modules with spanning sets xi, where I goes through some index set capital I, and yj, where j goes through some set capital J, respectively. So the xi generate M, the yj generate N. The tensor product, M tensor N, is spanned by the elementary tensors xi tensor yj. So if you know a generating set for M and you know a generating set for N, you know a generating set for the tensor product. Let's prove this. So what does an elementary tensor in M tensor N look like? It's some element little m tensor little n. And we know that the xi form a generating set for M. So this little m can be written as a finite R linear combination of these xi's. So a sum over I of ai times xi, where these ai's are ring elements, and all but finitely many of these ai's are 0. Same thing, we're going to write n as a finite R linear combination of these yj's. So a sum over j of bj times yj, where all but finitely many of these ring elements bj are 0. And since taking the pair m comma n to m tensor n is a bilinear map from m cross n to the tensor product, well, then what is m tensor n? Well, what is m? It's the sum of ai times xi. And what is n? It's the sum of bj times yj. But this is equal to a sum over all pairs I and j of the ring element ai times bj times the elementary tensor xi tensor yj. So what is this? This is a finite R linear combination of these xi tensor yj's. So you can think about this as following from the bilinearity of this tensor product map, or just from the basic properties of tensors that we saw when we were talking about the construction of the tensor product as a quotient of this big free module by this submodule D. So now we've seen that any elementary tensor is a finite R linear combination of these xi tensor yj's, these simple, these elementary tensors. And every tensor is a finite R linear combination of elementary tensors. We have seen in the previous lecture that the elementary tensors generate the tensor product as an R module. So what does that mean? This set of these special elementary tensors, xi tensor yj, these span m tensor n as an R module. So I'll pause and erase, and we'll talk about a particular case of this result, and then some stronger things that are true. We have seen that if you have a spanning set for an R module M and a spanning set for an R module N, you get a spanning set for the tensor product. So let's take the particular case where we have both of those modules M and N being the free R module of rank k, R to the k. What's a spanning set? Well, we have the standard basis vectors E1, E2 up through Ek. And we know now that the R module R to the k tensor R to the k is spanned by the k squared elementary tensors EI tensor EJ. So in fact, E1 up through Ek, this is a basis. And now we've constructed a spanning set. But it is true that this spanning set is also a basis. What do we need in order to see that it's a basis? Well, it's definitely a spanning set. We have to prove that this spanning set is linearly independent. And we'll come back and talk about that a little bit later. So the last thing I want to do in this video is prove a simple result about tensor products. So we have these simple tensors, and we have some special elements in our ring R. For example, the 0 element. So in M tensor N, if you take the elementary tensor M tensor 0, that's the same as the elementary tensor 0 tensor n, which is 0, by which I mean the additive identity of this R module. How does this proof go? This is just like the proof that a times 0 has to be 0 in a ring. So if you remember how that proof goes, this goes the same way. M tensor n is additive in n if we hold m fixed. So what does that mean? M tensor 0 is equal to m tensor 0 plus 0, right? Because 0 plus 0 is 0. And now, what does this mean, additive in n for fixed m? This is equal to m tensor 0 plus m tensor 0. So now we can subtract the element of our R module, m tensor 0, from both sides. And we see that 0 is equal to m tensor 0. Showing that 0 tensor n equals 0 is very, very similar. So this is the kind of argument that is very similar to something we've already seen. And now we're just rephrasing it in this new language of tensor products.